Good evening everyone, good evening. I welcome you all again to NEET Elite. Hoping that you guys are doing great, having a good time. So people, you can let me know in the chats first of all if I'm audible and visible to everyone. Good evening everyone, good evening. Hello Fazan, hello 5-star education. Hello Saja, hi Dakshin, hello Tanzila, hi Chitra, hello Sneha, Ubad, Ishpreet, Ashwarya, Afshan, Akash, Dakshin, Anil, Ubad, Sahil, Irfan, welcome back everyone, welcome back. Hello Arzu, hello Anil. I'm doing good, Ishpreet, better than before, but I'm not completely well. I've got cold cough going on, yeah. Hello Noreen, hi Jabisa, hello Samriddhi, welcome back. Hi Ashika, hello Rohit, hi Manjula, hello Umar. So welcome back people, welcome back, welcome back, welcome back. Just let me know in the chats first of all if I'm audible and visible to everyone. Yes, my day was good, Aishwarya, my day was good, thank you. So let me know fast in the chats, give me some green signal from the chat box so that I'll get to know that I'm audible and visible to you properly. Yes, let me know fast in the chats. I'm doing good, Sneha, I'm doing good. Give me some green signal from the chat box, people. Yes, am I getting the green signal from my NEET Elite people? Yes? Perfect guys, wonderful. So as you all must be knowing, in the last session, we started the molecular orbital theory, right? Which was, I told you, one of the most important theories as far as your chemical bonding is concerned. Okay, we could not finish that theory. In the tonight's session, I'll be starting, I'll be finishing that molecular orbital theory first, then we'll be doing the previous year questions which have been asked from this chemical bonding chapter in your different medical competitive examinations, right? Yes. So in the last session, if you remember exactly, I showed you how molecular orbitals are formed by the linear combination of atomic orbitals. Yes. And in the tonight's session, we are going to discuss a lot of things, okay, in that molecular orbital theory only, and we'll be doing the previous equations, right? Okay, without wasting a lot of your time, let's get going, let's get started. But before that, the ones who are new to the channel, let me introduce myself. Well people, my name is Wassim Bhatt and I'm your chemistry master teacher writer on this NEET Elite channel, right? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I take live on this NEET Elite channel, right? So do like the video, share the video with your friends and do subscribe to the channel as well, okay? Well, people are asking about the next chapter. Next chapter most probably is going to be General Organic Chemistry, GOC. Okay? Yes, Amanat, surely you can meet me. Alright, so people, you can let me know in the chats if you people are super duper excited about the tonight's session as well. Just let me know fast in the chats. Let me know fast in the chat so that I get to see the josh of the session. Yes? Yes, Rohit, from tomorrow I'll be doing the KVPY mock test as well on JEE Enthuse channel, right? At 10:30 in the night. So you guys can join in too. So tomorrow I'm going to take KVPY SA mock test 1, right? So from tomorrow, I'll continue the mock test for KVPY on the JEE Enthuse channel, right? You guys can join in. Perfect. Okay. So let's get going then. Let's get started with let's continue the molecular orbital theory, right? So people, till now, in the last session, we saw exactly how the bonding molecular orbitals and anti-bonding molecular orbitals are formed by the linear combination of atomic orbitals. If you remember, I told you molecular orbitals are formed by the interference of the atomic orbitals, right? Whenever there'll be a constructive interference leads to the formation of the bonding molecular orbital, right? And destructive interference, it leads to the formation of anti-bonding molecular orbital. Energy of bonding molecular orbital is comparatively less than that of energy of anti-bonding molecular orbital, right? Due to which stability of bonding molecular orbital will be definitely more than that of stability of the anti-bonding molecular orbital, right? That's something which we have discussed. We saw exactly how these molecular orbitals are formed, right? Since we got to know the molecular orbitals which get formed when the atomic orbitals combine, right? We got to know exactly. Now it is the time to fill electrons in those molecular orbitals and it is the time to calculate the bond order of different species, which is the very important concept, right? Have a look exactly what I'm going to talk about. Understand properly. So first of all, let me tell you, I have noted down the molecular orbitals right here, which got formed by the linear combination of atomic orbitals of two bonding atoms, right? Okay, I'm starting with sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, and sigma star 2pz. Well, the molecular orbitals which are formed by the combination of atomic orbitals of the bonding atoms, right? I will arrange those molecular orbitals on the basis of their increasing energies, right? This is the increasing energy order of the molecular orbitals, which you guys are going to remember, but this is valid for only that species which contains the electrons up to 14, right? What does that mean? See, first of all, the molecular orbitals which we got till now by the linear combination of atomic orbitals. Now, I'll arrange these molecular orbitals on the basis of their increasing energies. Now, I'll be filling these molecular orbitals on the basis of their increasing order of the energies as per Abba's principle is concerned, right? In atomic structure, we have discussed how to write the electronic configuration, yes? And in order to write the electronic configuration, you need to follow three rules: Abba's principle, Pauli's exclusion principle, and Hund's rule, right? Hund's rule of maximum multiplicity. The same rules I'm going to follow here in order to fill the electrons in these molecular orbitals. First thing, I'm going to fill these molecular orbitals with the electrons on the basis of their increasing order of the energies, right? As per Abba's principle, correct? Point number one. Point number two, every molecular orbital right here can accommodate maximum of 2 electrons, and those 2 electrons with the opposite spin. Every molecular orbital which we have over here, it is going to accommodate maximum of 2 electrons, that too with opposite spin, right? And at the same time, as you can look over here, pi 2px is equal to pi 2py. What does it mean? It means these two molecular orbitals, these are degenerate, they have got same energies. Similarly, pi star 2px, pi star 2py, these are again degenerate molecular orbitals having same energies, right? Okay, now let's have a look. Let's see exactly how this concept is used and how do we calculate bond order and how to write the molecular orbital electronic configuration of different species, right? Let's have a look exactly, guys. Let's start with hydrogen, H2 molecule. Let's start with H2 molecule, right? First of all, in case of hydrogen, hydrogen has got the atomic number of 1, right? So in one atom of hydrogen, you'll find 1 electron, right? But over here, we have got 2 atoms of hydrogen, so there'll be exactly 2 electrons present in H2. Similarly, in He2, in one helium atom, there'll be 2 electrons. In 2 helium atoms, there'll be 4 electrons. Similarly, Li2, there'll be 6 electrons in total. Similarly, Be2, there'll be 8 electrons in total, correct? Now, in case of H2, let me write the molecular orbital configuration for this H2 over here. Since H2 has got 2 electrons, right? And both these electrons will get accommodated in this sigma 1s, right? Sigma 1s2, sigma 1s2 becomes the molecular orbital configuration of H2 molecule, right? I hope you remember these starred ones. This is sigma star 1s, again star over here, they represent the anti-bonding molecular orbitals, if you remember. Yes. Now people, you got to know the molecular orbital configuration of H2. Let me calculate the bond order. As I told you in the last session, bond order has got the formula: half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital, which comes out to be half of. How many electrons are there in bonding molecular orbital? Since there are 2 electrons and both the electrons are present in the bonding molecular orbital, there is no electron present in anti-bonding, so 2 minus 0 comes out to be 2, 2 divided by 2 is 1. So bond order of H2 comes out to be 1, right? Bond order of H2 comes out to be 1. What does that mean? That means between 2 hydrogen atoms there is a single bond present. Between 2 hydrogen atoms there is a single bond present, right? Now have a look exactly. In this configuration, do you see any unpaired electron? Right? H2, it does not have any unpaired electron, right? See, every molecular orbital is going to accommodate maximum of 2 electrons. And both these electrons are present in this molecular orbital. So there is no unpaired electron. If there is no unpaired electron, that means this H2 molecule, it's going to be diamagnetic. It's going to be diamagnetic. Any species which contains unpaired electrons in its molecular orbital configuration it's supposed to be called as paramagnetic. Any species which does not have any unpaired electron in its molecular orbital configuration, it's supposed to be diamagnetic. Well, we are going to do the previous year questions as well. Just wait for it. Let me finish the topic first. After that, we'll be doing the previous year questions as well. No issues. Ayush, I think you have not seen the last lecture of molecular orbital theory, right? Go for it once, check it out. After that, you can join this session. You'll be understanding all this, right? But first, see the yesterday's session. Then only you can understand it, okay? So, now let's try to talk about He2. Since there are 4 electrons, right? Now I need to accommodate these 4 electrons in these molecular orbitals. 2 electrons are present in sigma 1s and there will be 2 electrons present in this sigma star 1s. So what is going to be its molecular orbital configuration? It's sigma 1s2, then sigma star 1s2, right? Sigma 1s2, sigma star 1s2. This is the molecular orbital configuration of He2, correct? Let's calculate the bond order of this helium, He2. If I talk about its bond order, half of number of electrons in bonding molecular orbital 2 minus number of electrons in anti-bonding molecular orbital 2, value comes out to be 0. In the last session I told you, in any species, if the bond order comes out to be less or equal to 0, that simply means the species does not exist. So remember, He2, this molecule does not exist at all, right? As simple as that, correct? Now have a look. If I talk about Li2, 6 electrons, right? 6 electrons. 2 electrons are already filled, 2, 2, 4, and 4 and 2 comes out to be 6, right? So 6 electrons. What about the configuration? Sigma 1s2, sigma star 1s2, and sigma 2s2, correct? This is the molecular orbital configuration of Li2 molecule. Let's calculate its bond order now. Its bond order is simply going to be half of number of electrons present in bonding. 2, 2 and 2 comes out to be 4, minus number of electrons in anti-bonding. 2 electrons in anti-bonding, so 4 minus 2 is 2, 2 by 2 is 1, right? So in case of Li2 molecule, the bond order is 1. That means there is a single bond between 2 lithium atoms. There is a single bond between 2 lithium atoms in case of Li2, yeah? Yes? Right? As simple as that. Now people at the same time, do you see any unpaired electron here? No, you're not seeing any unpaired electron here. Every molecular orbital is completely filled. So it's supposed to be diamagnetic. It's again diamagnetic, right? Okay. Now similarly, let's talk about Be2, right? 8 electrons in total. 2, 4, 6, and 8, right? Let's write the configuration. It's sigma 1s2. It is sigma star 1s2, right? It is sigma 2s2. And at the end, you have got sigma star 2s2 as well. Sigma star 2s2 as well, correct? Let's talk about the bond order of this molecule. It's going to be equal to half of number of electrons in bonding molecular orbital, which is 2, 4, right? Number of electrons in bonding molecular orbital minus number of electrons in anti-bonding, 2 and 4, right? So 4 minus 4 comes out to be 0. This bond order comes out to be 0, and any species which will be having 0 bond order, it does not exist. As simple as that, right? Yes, people? I'm sure it's clear to everyone. So this B2 does not exist at all, right? Okay, I'm sure till here it's clear to every single guy, right? Let's talk about few more molecules. These are few more molecules which I'm going to talk about. If I talk about B2, boron has got the atomic number of 5. That means in one atom of boron there are 5 electrons. So in 2 atoms of boron there will be 10 electrons. Similarly, C2, there will be total 12 electrons. N2, there will be total 14 electrons. This is N2 with a positive charge. That means in N2 1 electron has been taken out, right? N2 has got 14 electrons and 1 electron has been taken out, so 13 electrons in total in case of N2 positive. Similarly, N2 negative, there will be total 15 electrons, right? Yes? Basically, N2 got 1 extra electron, N2 already has 14, now extra 1 electron, it comes out to be 15, right? Now let's try to write the molecular orbital configuration. 10 electrons, I'm going to fill on the basis of the increasing order of the energies. This is 2, 2 to 4, 4 to 6, 6 to 8, 6 to 8, right? Now, 2 electrons are left. Since these 2 molecular orbitals, these are degenerate molecular orbitals, right? As per Hund's rule, pairing won't happen unless each degenerate orbital gets 1 electron each. So I'll keep 1 electron here, I'll give 1 electron here, right? Pairing won't happen in the degenerate orbitals unless each electron gets, unless each molecular orbital gets 1 electron each. As simple as that, as per your Hund's rule of maximum multiplicity is concerned, right? Now guys, have a look. So let's calculate the bond order. See, you got to know the molecular orbital configuration of B2. It's sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px1, pi 2py1, right? Let's calculate the bond order. bond order is simply going to be half of number of electrons in bonding molecular orbital 2, 4, 5, 6 minus number of electrons in anti-bonding molecular orbital 2, 4, right? 6 minus 4 comes out to be 2. 2 divided by 2 comes out to be 1. So bond order of B2 comes out to be 1, right? Bond order of B2 comes out to be 1. So basically there is a single bond between two boron atoms, right? Now understand. If you look at the molecular orbital configuration of this B2, do you see the unpaired electrons? Yes, people, you are seeing the two unpaired electrons, right? Because we know every molecular orbital can accommodate a maximum of 2 electrons. Since it contains only one, it contains only one. So there are 2 unpaired electrons in case of B2, right? If there are 2 unpaired electrons, that clearly says this B2 is going to be paramagnetic. This B2 is going to be paramagnetic, right? And for paramagnetic species, we calculate spin magnetic moment. I hope you remember in your atomic structure, we have discussed this too. And what is the formula to calculate spin? It is under root of n into n plus 2 Bohr magnetrons, right? N represents the number of unpaired electrons. N represents the number of unpaired electrons. So how many unpaired electrons do we have? 1 plus 1, 2. So n value is 2 over here. So it's going to be 2 multiplied by 2 plus 2. 2 plus 2 is 4. 4 2s are 8. So root of 8 is going to be the value of spin magnetic moment for this B2 molecule over here. This is the formula by means of which you can calculate the spin magnetic moment, right? As simple as that. Let's talk about this C2 molecule. C2 molecule is that it has got some 12 electrons. And already till now, we have filled some 10 electrons, right? Now it's time to fill 2 more electrons. So I'll keep 1 here. I'll keep 1 more here, right? So I've filled 2 more electrons, correct? Now have a look. Let's calculate the bond order now. Bond order will come out to be half of number of electrons in bonding. 2, 4, 6, 8. So 8 electrons in bonding molecular orbitals minus anti-bonding 2, 4. So 8 minus 4 comes out to be 4. 4 by 2 is 2. That means between 2 carbon atoms there will be a double bond, right? That means between 2 carbon atoms there will be a double bond, right? Okay. So people, in case of C2, there will be a double bond. There will be a double bond between 2 carbon atoms. And remember, this is a special case. This C2 is a special case in which both these bonds are going to be pi bonds, right? It's not going to be 1 sigma and 1 pi. In case of C2, both the bonds are going to be pi bonds, right? Why both the bonds are going to be pi bonds? Because if you look at the outermost molecular orbital configuration, right? In case of the outermost molecular orbital configurations, there are 2 electrons in pi 2px and there are 2 electrons in pi 2py. So it is going to form 1 pi bond, it's going to form 1 pi bond, 1 more pi bond. So basically 2 pi bonds are being formed in case of C2 molecule. It's a special case in which both the bonds are going to be pi. Yes, as simple as that. Okay, so if I ask you, is this C2 molecule going to be paramagnetic or diamagnetic? See, there is no unpaired electron as such. If there is no unpaired electron as such, it's absolutely going to be diamagnetic, right? Similarly, let's talk about N2 containing 14 electrons. So till here, we have filled some 12 electrons. So 12 and 2 will be 14, right? So this becomes the molecular orbital configuration of N2. Yes. Now, let's calculate the bond order. Let's calculate the bond order. It's going to be half of number of electrons in bonding. This is 2, 2 to 4, 4 to 6, right? 6 to 8, 8 to 10. So there are 10 electrons in bonding molecular orbitals, right? Minus anti-bonding, 2 and 2, 4. So 10 minus 4 comes out to be 6, 6 by 2 comes out to be 3. That means in case of N2 molecule, there's a triple bond between 2 nitrogen atoms, right? So it's going to be N triple bond N. It's going to be N triple bond N, correct? It's going to be simply N triple bond N. You can take it out. 1 is going to be sigma bond and 2 are going to be pi bonds. This is responsible for the sigma bond and these two are responsible for making pi bonds, right? This is pi 2px2, this is pi 2px2, this is sigma 2pz2. So this molecular orbital is responsible to form the sigma bond, this one is responsible to form the pi bond, and this one is again responsible to form the pi bond, right? Hello, Hejaz Mukhtar, how are you? I'm sure it's clear to everyone, right? Now people, let's talk about N2 positive. There are some 13 electrons only, right? There are some 13 electrons. If there are 13 electrons, let's try to adjust these 13 electrons. Have a look. 2, 4, 6, 8, right? 9, 10, 11, 12 and 13, right? So first thing, before calculating the bond order, I'll ask you, is this species going to be paramagnetic or diamagnetic? This N2 positive, is it going to be para or dia? See, there is one unpaired electron, so it's absolutely going to be paramagnetic, right? This N2 positive, it's going to be paramagnetic. It's going to be paramagnetic, right? As simple as that. Similarly, if I want you guys to calculate its bond order, you can follow the same procedure, half of number of electrons in bonding and anti-bonding minus anti-bonding, you'll be getting the bond order of 2.5. You will be getting the bond order of 2.5, right? As simple as that. Similarly, if I ask you to calculate the spin magnetic moment of this N2 positive, you'll write spin magnetic moment of N2 positive is going to be under root of N into N plus 2 Bohr magnetrons, right? Well, people, N represents the number of unpaired electrons, and there is just one unpaired electron. So 1 multiplied by 1 plus 2, 2 plus 1 is 3, 3 multiplied by 1 is 3. So this is root of 3 Bohr magnetrons. This is the spin magnetic moment of this species, right? Similarly, when you calculate for N2 negative, N2 negative contains 15 electrons. But you are saying over here, this is the electron filling order up to 14 electrons, right? But over here it has got 15 electrons. So how can we use this molecular orbital configuration for this species which contains 15 electrons, right? It's simple, guys. See, this N2 negative, it is derived from N2. It is derived from N2, and N2 contains 14 electrons, right? So if N2 contains 14 electrons, for N2 we are going to follow this order, and for its N2 negative, for its derived species N2 negative, right? For N2 negative, again we are going to follow the same order only. Yeah? Have a look. It's again going to be, when you calculate it, when you write this molecular orbital configuration, you can calculate its bond order. It will again come out to be 2.5 only, right? And you can calculate then its spin magnetic moment, everything. Okay? I'm sure it's clear to everyone. Yes? Perfect. Okay, now let's move on to the calculation of bond order of the species which contains more than 14 electrons. Right? Till now I was talking about the species which contains less or equal to 14 electrons, correct? Now I'm going to talk about those species which contain the electrons greater than 14, correct? And for those species, this is going to be the order which you guys are going to follow, as simple as that. Do remember this order, and this is valid for the species which contains the electrons more than 14. Yes, as simple as that, right? Yes, Hari Kishore, next chapter is going to be this general organic chemistry. Yes, absolutely. Okay, let's take a few more examples for this so that we can wind it up, this molecular orbital theory, and then we can do some previous equations which have been asked from this chapter. Yeah, perfect. Abrar, which standard you're talking about? Okay. See guys, let's talk about O2. O2 contains total 16 electrons, right? Right, because in one oxygen atom, there are 8 electrons. Yes, in 2 oxygen atoms, there will be 16 electrons, right? So there are 16 electrons in total. Let's try to fill these. So 2, 4, 6, 8, 9, 10, 11. Sorry, what did I do? Okay, 2, 4, 6, 8. This will be 10, 11, 12, 13, 14, 15, 16, right? Okay, so this is going to be its molecular orbital configuration for O2. So first thing, do you see any unpaired electrons? Yes, absolutely, we are seeing 2 unpaired electrons, right? So absolutely this O2 is going to be paramagnetic. First thing, it's going to be paramagnetic, right? If it is paramagnetic, let's calculate its bond order now. Bond order is simply going to be half of number of electrons in bonding molecular orbital, 2, 4, 6, 8, 10, right? So there are 10 electrons in bonding molecular orbital minus anti-bonding, 2, 4, 5, 6. So 10 minus 6 comes out to be 4, 4 by 2 comes out to be 2. So bond order of O2 is coming out to be 2. That clearly says there is a double bond between 2 oxygen atoms, as simple as that, right? There is a double bond between 2 oxygen atoms, as simple as that. Yes? So, if I ask you to calculate its spin magnetic moment, you can do that, right? Spin magnetic moment, we get by the formula under root of n into n plus 2. N value, number of unpaired electrons, 2 multiplied by n plus 2, right? 2 plus 2, 4, 4 2s are 8. So, root of 8 Bohr magnetrons is going to be the spin magnetic moment of this O2. Yes? Right? Similarly, guys, you can calculate for O2 positive, you can calculate for O2 negative, you can calculate for O2 di-negative, right? You can do that. And this is going to be your homework. Right? This is going to be your homework. Let me tell you one more trick as well to find the bond order without using this formula. Without using all these formulas, let me tell you one trick which you can remember in order to calculate the bond order of different species, okay? Yeah? This is something which you can do on your own by application of formula, by filling these orbitals and everything, right? Let me show you one general trick. Remember guys, any species which contains 14 electrons is always going to have the bond order of 3. Any species which contains 14 electrons, any species, be it N2 or whatever, any species which contains 14 electrons is going to have bond order of 3. So over here I'm writing 13 electrons, then I'm writing 12, then I'm writing 11, then I'm writing 10, right? Over here I'm writing 15, I'm writing 16, I'm writing 17, I'm writing 18, right? Okay, so this is 3. Just reduce it by half, it becomes 2.5. Reduce it by half, it becomes 2. Reduce it by half, 1.5. Reduce it by half, 1. Right? Similarly, when you go up, reduce it by half, it's 2.5. Reduce it by half, it's going to be 2. This is going to be 1.5. This is going to be 1. These are the bond orders of different species containing 10 electrons, 11, 12, 13, 14, 15, 16, 17, 18, and so on. Right? And do remember, in case of O2 containing 16 electrons, 16 electron species contains 2 unpaired electrons. Right? 16 electron species is going to contain 2 unpaired electrons, correct? That means in 15 electron species, there is 1 electron less, it's going to contain 1 unpaired electron. Similarly, in case of this 14 electron species, correct? There'll be no unpaired electron. Do remember this as well. Similarly, in 17 electron species, if in 16 electron species there were 2 unpaired electrons, right? Now in 7 electron species, there'll be only 1 unpaired electron. Do remember this as well, correct? Yes, as simple as that. Right? Do remember all this. Do remember all this, my dear elites. Yeah? I saw you in one college in one video. Sanjay, which college was it? Was it Jipmer Medical College? Yes? Because I've done many shows in Jipmer Medical College. Even in SRM University. Even in Kilpauk Medical College, right? Yes, and a lot of different colleges in Bangalore as well. During my college days, I mean, yeah? You might have seen that video on the YouTube. People, is everything clear till now? I'm sure it's clear, right? Abrar, what are you talking about? Okay, so I assume everything is clear. Now. Let me tell you one more important thing. People, we have discussed something called as isoelectronic species in atomic structure. Isoelectronic species are the ones which have got the same number of electrons, right? Which have got the same number of electrons, correct? You all know it. For example, if I talk about NO positive and Cn negative, NO positive and Cn negative, right? Nitrogen contains 7 electrons, oxygen contains 8, so 7 plus 8 comes out to be 15, and there is a positive charge, so 15 minus 1 comes out to be 14. So 14 electron species this is. Similarly, carbon contains 6, nitrogen contains 7. So 7 plus 6 is 13, 13 and negative charge comes out to be 14. So these two species, again, these are what? They contain same number of electrons, so these are going to be isoelectronic. And remember, whenever I'll be having the isoelectronic species, they are going to have always the same bond order. So their bond order will be the same because these are isoelectronic species. And I told you a few minutes back only. And anyways, you can talk about N2 as well, right? N2 also contains 14 electrons. And all the 14 electron species, they have got the bond order of 3. Correct? So remember, whenever you see the isoelectronic species, they'll be always having the same bond order. Yeah? Right? People? Absolutely correct. Isoelectronic species always are going to have same bond order. Okay? Now, if I ask you about one more thing, I'll ask it to you. Okay? I'll ask it to you. For example, I'm giving you 3 species. One is N2, one is N2 positive, and one is N2 negative. Right? When you write their molecular orbital configurations and when you find their bond order of this species will come out to be 3, this species will come out to be 2.5, this species will come out to be 2.5, right? This is something which I'm telling you. You can check it out as well. You can write their molecular orbital configurations, which we have already written, right? We have already calculated the bond order of these species over here, right? Before a few minutes back only. Yeah? Okay, now I'm going to ask you one thing. Okay, before asking one thing, let me tell you, bond order is directly proportional to the stability of the molecule, stability of the diatomic molecule. More the bond order in the diatomic molecule, more is going to be the stability of the molecule. Why is that? What does that mean? More the bond order means more will be the bonds present between the atoms. And if more are the bonds present between the atoms, that means more is the force of attraction. If more is the force of attraction between the atoms, more is the energy needed to break it. That means more is going to be the stability, as simple as that, right? So more the bond order, more the stability, correct? Now, if I ask you to arrange these, first, second and third, if I want you guys to arrange these on the basis of their stabilities, You'll clearly say this N2 has got the maximum bond order, so it's going to be maximum stable, right? Now, this is having 2.5 bond order, this is having 2.5 bond order. So the stability of these two must be same then, right? So the stability of these two must be same, which is not the case. Stability of these two is not the same. Stability of these two is not the same. Why is that? Why is that? What is the reason for that? What is the reason for that? You can let me know in the chats. I'll be waiting for your answers. I will be waiting for your answers. Let me tell you, the stability of N2 positive is going to be more than that of N2 negative, right? Why is that? Remember, whenever you'll be having two species having same bond order, whenever I'll be having two species having same bond order, how to compare their stabilities? How to compare their stabilities? Remember, that species among the two which contains less number of electrons in anti-bonding molecular orbitals. That species among the two which contains less electrons in its anti-bonding molecular orbitals is going to be more stable. In the last session, I told you, if you remember. In the last session, when I gave the postulates of bonding, this molecular orbital theory, I told you in the last session, whenever I'll be having two species having the same bond order, remember, the one containing less number of electrons in anti-bonding molecular orbitals will be more stable. And there are definitely less number of electrons in anti-bonding molecular orbital in N2 positive than that of N2 negative, right? Do remember this thing as well. Due to which this is actual stability order. Yeah? Okay? I'm sure it's clear to everyone, right? So, I assume all this is clear, right? So people, are you guys ready for the previous year questions now? Are you guys ready for the previous year questions? Let's check it out. What kind of questions have been asked from this chapter? Are you guys ready for it? Let me know fast. I've only come up with those questions which have been asked from this chapter in different medical competitive examinations. I'm not going to do the JEE questions here, right? JEE questions I'll be doing on the JEE channel. NEET questions, AIPMD questions, AIMS questions, like whatever medical competitive examinations are there, right? Whatever questions have come from this chapter in different medical competitive examinations, I'll come up with those questions only, yeah? Are you people ready for it? And you guys are going to let me know the answers now, okay? I'm not going to do them. You guys are going to let me know the answers because I've discussed all the concepts which are required to solve these questions. Yeah? Perfect, guys. Right? Okay, so let's move on then. This is the simplest question among all. The question has been asked in NEET 2013. Which of the following is electron deficient? Electron deficient. What do you need to see? You need to see the octet. You need to see, okay, let me not go into the details. Okay, which of the following is electron deficient? You guys let me know in the chats fast. Let me know in the chats fast, people. Let me know in the chats fast. Well, I can see people are coming up with option B, and let me tell you, all of you are perfectly correct. It's going to be option B, which is going to be electron deficient. Absolutely, people, right? Okay. Yes. BH3 twice, or you write as B2H6. It's called as, what do we call this as? It's called as diborane. This diborane, this is something which you will discuss in P block elements. I'm not sure whether you have discussed it or not. In this diborane, you have got two 3-centered 2 electron bonds. This is what we call as 3-centered 2 electron bond. This is what we call as 3-centered 2 electron bond, or you call them as banana bonds as well. So there are 2 banana bonds in this case. There are 2 3-centered 2 electron bonds in this case, right? This is 2-centered 2 electron, 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 right? This is something which we are going to actually discuss in P block when I'll teach you that, right? Let's not go into the details. Okay? Correct? Well, anyways, majority of the students have given the correct answer. I appreciate it. Okay, one more question, AIPMD 2000. Cation and anion combines in a crystal to form which type of compound? People, is it a question? Yeah? Let me know first in the chats. What is going to be the answer of this one? What is going to be the answer of this one? I have discussed, right? Yes, electrovalent bond, ionic bond, right? Which is basically the electrostatic force of attraction between the cation and the anion, right? Okay, and any compound which contains the ionic bond is what we call as ionic compound, as simple as that. So cation and anion, they combine in a crystal to form which type of a compound? It's absolutely going to be ionic compound, right people? We have discussed this in the first session if you remember. Moving on to one more. Among the following, the electron deficient species is. Again, you guys are going to check. Which of the following is electron deficient? Let me know fast in the charts. Let me check the octet of this boron. This boron is forming 3 bonds, right? So there are only 6 electrons in the outermost shell of boron. But as per octet rule, it should have 8. So this electron deficient, as simple as that. BCl3 is electron deficient. It should have 8 electrons in its valence shell, but it's only having 6, right? So this BCl3 is absolutely electron deficient, right people? So option A is going to be the correct answer of this question. Going on to one more. Which of the following, among the following, which compound will show the highest lattice energy? The question was asked in AIPMT. My God, 1993. 1993, 2 years before I was born. Among the following, which compound will show the highest lattice energy? As I have told you people, when I taught you the lattice energy, I told you lattice energy, it depends on the charge and it depends on the size of the ion as well. Correct? See, everywhere you have got same anion. Everywhere you have got same anion. So I'm not going to decide on the base of anion. I'm not going to decide on the base of anion because everywhere you have got same anion. Point number 1. Point number 2. This is K positive, this is Na positive, this is CS positive, this is Rb positive. I'm not going to decide on the base of charge on the cation because charge on every cation is same. Because charge on every cation is same, right? Now, I'm going to decide on the base of size of the cation. Wherever size of cation is going to be least, there only lattice energy is going to be highest, right? And if you remember, on moving from top to bottom, Li positive, if I talk about Na positive, then I talk about K positive, then I talk about Rb positive, then I talk about CS positive. As we move from top to bottom, what happens to ionic size? Ionic size increases, right? So this one is not given in our options, right? So Na positive will have the least size among all, right? If Na positive has got the least size among all, so its lattice energy over here, lattice energy of this compound is going to be maximum, as simple as that, right? Right people, let me know in the charts if it is clear. Let me know fast in the charts if it is clear to everyone. Right? Perfecto. Let's move on to one more then. Okay, which of the following formulae does not correctly represent the bonding capacities of 2 atoms involved? AIPMT question. Let me know its answer. Fast. Fast. Fast guys. Which one of the following formulae does not correctly represent the bonding capacities of 2 atoms involved? Well people, if you look at the last structure, if you look at the last molecule, see how many bonds this carbon is forming over here. It's forming 1, 2, 3, 4, 5. Have you ever seen carbon forming 5 bonds? No way, right? Maximum carbon can form 4 bonds. And over here, carbon is forming some 5 bonds. Is it possible? No way. So this is going to be my answer. Right? This is the incorrect representation. Right, people? Perfectly done. Moving on to one more. Which of the following is the correct order of dipole moment? See guys. Dipole moment. See, one of the species is first of all BF3. And you know, BF3 is the molecule having 0 dipole moment. Similarly, CH4 is the molecule having 0 dipole moment. Similarly, carbon dioxide is the molecule having 0 dipole moment. Similarly, BCl3 is the molecule having 0 dipole moment, right? These are all the molecules having 0 dipole moments, right? Okay. Yes. We have discussed all this in detail. I hope you remember that. These are all the common species which have got 0 dipole moments, correct? Which of the following is the correct order of dipole moment? So first of all, we are given with BF3. BF3 will be having the least dipole moment, that is 0. Right? BF3 is going to have 0 dipole moment, right? So answer is going to be either this one or this one, right? Now, among NF3 and NH3, we have discussed this example also. Among NF3 and NH3, which one is going to have more dipole moment? Check it out. Let's check it out again. Anyways, I've discussed this long back, so I'm not sure whether you remember it or not. So let's try to check it out again. Let's try to check it out again. If I talk about NH3 and NF3, and if I ask you which one is going to have more dipole moment, people, let's check it out, right? Let's check it out. Have a look. See, first of all, there will be the contribution of the lone pair towards the dipole moment, and the direction of dipole moment due to the lone pair is towards the lone pair. is towards the lone pair, correct? Now among nitrogen and hydrogen, which one is more electronegative? Nitrogen. So it will attract the bonded pair of electron towards itself, due to which nitrogen gets slight negative, hydrogen gets positive charge. So positive towards negative. Similarly positive towards negative. Similarly positive towards negative. So all the dipole moments are pointing upwards, right? So net dipole moment is going to be in this way. But if you look at this NF3, nitrogen and fluorine, fluorine being more electronegative, so negative charge on fluorine, positive charge on nitrogen, so from positive to negative, similarly positive to negative, similarly positive to negative. See, 3 dipole moments are pointing downwards, 1 dipole moment is pointing upwards, so there'll be some cancellation of these vectors, right? There'll be some cancellation of these vectors, so I can clearly say dipole moment of this NH3 is more than that of NF3, okay? So dipole moment of NH3 is more than that of NF3, so NH3 dipole moment is more than that of NF3, correct? So this one is the answer. Right? I'm sure it's clear to everyone. Perfectly done. Moving on to one more then. Which of the following molecules has the maximum dipole moment? Carbon dioxide will have 0 dipole moment, CH4 0 dipole moment, right? Among NH3 and NF3, few seconds back we have seen this. NH3 has got more dipole moment than that of NF3. So option C is going to be the answer, right? Okay, which of the following is a polar molecule? Check it out, guys. Which of the following is polar molecule? Which of the following is going to be polar molecule? See, SiF4, tetrahedral, right? Okay. Polar molecule is the one, non-polar molecule is the one which has got the net dipole moment 0. I hope you know that. Non-polar molecule is the one which has got the net dipole moment 0, right? See, SiF4, it's going to be perfectly tetrahedral, like your CH4. And in CH4, the dipole moment is 0. In SiF4, dipole moment is also 0, right? XCF4, correct? XCF4, it has got square planar geometry, and there'll be 2 lone pairs present at the axial positions, right? So the net dipole moment of this molecule is also 0. It's going to be non-polar. BF3, we know net dipole moment is 0, non-polar. So there is only one option left, SF4, right? There's only one option left, that is SF4, which is going to be polar, people. As simple as that, right? We can check it out as well, right? We can check it out as well. So it's going to be SF4. See, in case of SiF4, it has got the perfectly tetrahedral geometry. Yes. So since due to its symmetry, its net dipole moment is 0. So it's going to be non-polar. If you talk about XCF4, this is xenon, this is fluorine, one more fluorine on this side, one more fluorine on this side, right? Let's join them all. There's a lone pair present on the axial position, one more lone pair present on the axial position, right? So dipole moment due to this bond will be cancelled out by the dipole moment of this bond. Similarly, dipole moment due to this bond will be cancelled out by this. Similarly, dipole moment due to this lone pair will be cancelled out due to this, right? So its net dipole moment is 0 again, correct? And BF3, every one of you knows it, right? Okay, moving on to one more. Which of the following has more than one lone pair? Well, I can see XCF2 is the one. Check it out. If you look at XCF2, xenon, it has got some 8 valence electrons, right? It is forming some 2 sigma bonds. As you can see, 2 terminal atoms. That means 2 sigma bonds. So out of 8 valence electrons, 2 electrons this xenon is using to form 2 sigma bonds. So there'll be 6 electrons left as such on xenon in the form of lone pairs, right? So there are 3 lone pairs on xenon, correct? So it's absolutely going to be XCF2, which contains more than 1 lone pair, right? I'm not going to check the rest because I know the answer, right? AIMS 2016 question, right? Anyways, you can check the structures as well if you want it. Well, we have discussed all these molecules when I taught you the VSEPR, right? When I taught you about the shape, geometry, everything. Yeah, we have discussed all this in detail. Perfect. Okay, in the structure of ClF3, the number of known lone pair of electron on the central atom, chlorine. So the question was asked in NEET 2018. Wow. ClF3. First thing, how many valence electrons are there with chlorine? 7, because it's a halogen, right? How many sigma bonds are being formed? Since there are 3 terminal atoms, so 3 sigma bonds. So chlorine had some 7 valence electrons, and out of 7 valence electrons, it is using 3. So chlorine will be having some 4 valence electrons as such, which have not participated in the bonding. So there are basically 2 lone pairs, right? That's all. There are 2 lone pairs on chlorine. Yes? We have discussed this too. I hope you remember. Right? Let's move on to one more. Which of the following is isoelectronic and isostructure? Isoelectronic means same number of electrons. Isostructural means same hybridization. Check the hybridization. Isostructural means having same structure, having same geometry. Correct? Check it out. So if I got the answer. Well, if you check at this one, if you look at this one, check, are these two species having same hybridization? Are these two species having same hybridization? Check it out. If I talk about IBr2 negative, right? IBr2 negative. First of all, this is the central atom. It has got some 7 valence electrons, but the negative charge, so 7 plus 1 comes out to be 8. There are some 2 sigma bonds because it has got some 2 terminal atoms, right? How many lone pairs are there? Out of 8 valence electrons, it's using 2. So 6 electrons will be left as such. So 3 lone pairs. 2 sigma bonds, 3 lone pairs. Steric number comes out to be 5. And when the steric number comes out to be 5, hybridization is going to be sp3d. As simple as that. Similarly, in case of XCF2, hybridization is also going to be sp3d only, right? So these two have got same hybridization. They have got same geometry. So they are going to be isostructural. So whenever from now onwards, you will have to see which of the species are going to be isostructural. You'll be checking their hybridization. If their hybridization is same, they're going to be isostructural, right? If their hybridization is same, they're going to be isostructural. That's all. Okay. Maximum bond angle at nitrogen is present in which of the following? NEET 2015. Well, I can see the answer must be NO2 positive. Why is that? Have a look. See, nitrogen has got some 5 valence electrons, but there is a positive charge, so 5 minus 1 comes out to be 4. So there are some 4 valence electrons with nitrogen. Okay. So in case of NO2, if I make the rough structure, this is the rough structure of NO2. So out of 4 valence electrons, nitrogen is using 1, 2, 3, 4, right? Yes. Out of 4 valence electrons, nitrogen is using all its 4 valence electrons to form 4 sigma bonds. So there'll be no lone pair. Right? Well, how many sigma bonds it's forming? 1 and 2. 2 sigma bonds. Correct? Because terminal atoms are 2. 2 sigma bonds, 0 lone pair. What about the steric number? Steric number is going to be 2. If steric number is 2, hybridization is sp. If hybridization is sp, the bond angle is always going to be 180. In case of sp hybridization, the bond angle is 180. sp2, bond angle is 120. sp3, bond angle is 109 degree, 28 minutes, and so on, right? So as the hybridization moves from sp to sp2, then sp3, and so on, the bond angle keeps on decreasing, right? So maximum bond angle is possible in case of sp, which is 180 only, yeah? So B is going to be answer of the question. No need to check the rest. Well, you can check them out on your own, right, afterwards. No issues at all. Perfect. Which of the following pair, okay, in which of the following pair both the species have got the sp3 hybridization? In which of the following pair both the species have got the sp3 hybridization? We need to check one by one, right? Well, I got the answer. It is NF3 and water. If you look at the NF3 structure, nitrogen has got 1 lone pair and there are some 3 fluorine atoms. Correct? So 3 sigma bonds, 1 lone pair, so 3 plus 1, 4, hybridization is sp3. Right? In case of water, you know its structure. This is hydrogen, there is 1 lone pair over here, there is 1 lone pair over here. So 2 sigma bonds, 2 lone pairs, steric number 4, steric number is 4, that means hybridization again sp3. That's all. Right? So this is the answer. Yes? NEET 2013. Right? And I have already taught you how to calculate the lone pairs, sigma bonds and everything. That's something which I've discussed in detail, right? That's why I'm going a little fast over here, yeah? Because we have discussed all these concepts and I'm sure you know them. XCF2 is isostructural with, okay, if you look at XCF2, there are 2 sigma bonds, and there are 3 lone pairs. Right? So steric number will come out to be 5. So hybridization is going to be sp3d. Now I need to see among which of the following compound hybridization is sp3d. It's going to be ICl negative, ICl2 negative. It's going to be sp3d. Because few minutes back we saw the structure. We saw the hybridization of IBr2 negative. I hope you remember. This ICl2 negative is same as that of IBr negative only. So whatever is going to be hybridization of this one, same is going to be hybridization of this one. Even same is going to be the hybridization of I3 negative as well. sp3d, sp3d, sp3d. This one also sp3d, right? You can check it out. Perfect. Right, my dear elites. Okay, in which of the following species the central atom has got the type of hybridization which is not the same as that present in other 3, AIPMT? Well, SF4, it's going to have sp3d hybridization. When you check it out, you can check it out. 4 sigma bonds, 1 lone pair. Steric number 5, sp3d. I3 negative, few minutes back I told you, sp3d, right? PCl5, sp3d, right? In case of SbCl5 dinegative, it's not going to be sp3d, right? There are some 5 sigma bonds when you check it, 5 sigma bonds, and there is a lone pair, so 5 plus 1, 6. So hybridization is going to be sp3d2 in this case, right? So C is going to be answer of the question. C is going to be answer of this question, right? Yes? Okay, one more. Which of the following is not isostructural with SiCl4? Which of the following is not isostructural? Be careful with this. Not. SiCl4. Silicon comes in carbon family. Carbon family has got 4 valence electrons, and it is using all these 4 valence electrons to form 4 sigma bonds. So no lone pair on the central atom. 4 plus 0, steric number is 4. Hybridization is sp3, right? I need to say which of the following species does not have the sp3 hybridization. Which of the following species does not have the sp3 hybridization? Well, SO4 dinegative, it has got the sp3 hybridization when you check it out. PO4 trinegative, it will be having NH4 positive, absolutely it will be having SCl4 negative. There are 4 sigma bonds and there is 1 lone pair on sulfur when you check it out. So 4 plus 1, 5. Steric number is 5. When the steric number is 5, the hybridization is sp3d. So my correct answer is going to be option D. Option D is the answer. Well, already majority of the students have written option D as the answer. Wonderful. That means you have got all the concepts perfectly done. Moving on to one more then. Let's see if you have more questions. Yes. In an octahedral structure, the pair of d orbitals involved in d to sp3 hybridization. People, I have discussed, I have told you, in case of sp3d hybridization, which d orbital is involved in the hybridization? It's dz square, right? In case of sp3d2 hybridization, which all d orbitals are involved in hybridization? It is dx square minus y square and dz square. And similarly, in case of sp3 d3 hybridization, which d orbitals are involved? It is dxy, dyz and dzx, right? This is something which I've told you already. So in case of d to sp3, right, which d orbitals are involved in hybridization? No, it's going to be dx square minus y square and dz square. So option A is the one which is correct. Yes? Perfectly done again? Good job. Moving on to one more. This is one more. Okay, ASF5. ASF5. AS, arsenic, comes in nitrogen family. Nitrogen family has got some 5 valence electrons and it's using all these 5 valence electrons to form 5 sigma bonds. So there are 5 sigma bonds, there is no lone pair, so hybridization is sp3d. So in case of sp3d hybridization, which all orbitals are involved in hybridization? It is S. There are some 3 p orbitals, which is going to be px, py and pz, right? And there is a d orbital involved as well, and which d orbital is going to be dz square. So these are the orbitals involved in hybridization, right? Check it out. S, px, py, pz and dz square. So option C is the one which is correct. AIPMT 1997. Yes? Perfect? Perfect, guys? Okay, identify the molecule which does not exist. Few minutes back only we have solved this, right? NEET 2020 question. Few minutes back I've told you the concept, right? That species in which the bond order comes out to be less or equal to 0, we say that does not exist. And in case of He2, in case of helium He2 molecule, its bond order comes out to be 0, right? There are 2 electrons in bonding and 2 electrons in anti-bonding. So 2 minus 2 divided by 2, that comes out to be 0. Yes? So it does not exist. Few minutes back only we have seen. Which of the following is paramagnetic? Any species which contains unpaired electrons will be paramagnetic, right? NEET 2019. O2 is the species. When you write its molecular orbital configuration, there will be 2 unpaired electrons in pi star molecular orbitals, right? There will be 2 unpaired electrons in pi star molecular orbitals. So there are 2 unpaired electrons in O2, right? So it's going to be absolutely paramagnetic. Well, if you check all the others, they are going to be diamagnetic. All the other species, they do not have unpaired electrons in their molecular orbitals. As simple as that, right? So option A is the correct answer. And you can calculate its spin magnetic moment as well. Under root of n into n plus 2, n value is 2. So 2 into 2 plus 2, 2 plus 2 is 2, 4, 4 2s are 8. So root of 8 Bohr magnetrons is going to be the spin magnetic moment as well for this O2. We have discussed this in detail few minutes back only. Okay, the correct bond order in the following species. This is going to be your homework. Please and please do let me know the answer of this question in the comment section. And this was the last question of the tonight's session, right? Okay, so please and please do let me know in the chats, in the comment section, what is going to be the order of, what is going to be the answer of this question, the correct bond order, right? This is O2 dye positive, O2 negative, O2 positive. Do let me know the answer of this question. And this question was asked in NEET 2015, and I'm sure you're going to kill it, right? Yes. So at the end, let me tell you one interesting thing. There is the EdTech Fest going on in Vedantu, right? Which is there for one more day. And people, you are getting 50% off in all the subscriptions. Whatever subscription you want to take, you can take it by applying the coupon code and get 50% off, right? In whatever subscription you take, right? For example, majority of you guys are preparing for NEET 2023, right? So for this NEET 2023, we have come up with 3 plans for you. One is Light, Classic and Plus, right? These are basically the 2-year classroom programs in which you are going to get trained by us in all the subjects in the actual Vedantu platform, not on the YouTube, on the actual Vedantu platform, right? Okay, those are some special classes basically, right? Okay, apart from the YouTube sessions. Well, people, these are the course fee in these pro subscriptions, and these course fee, these are the 2-year packets, right? This is the course fee for complete 2 years, complete 2 years. Choice is all yours, whichever you want to take. Point number 1. Point number 2. Well, you don't need to pay this much of amount in one go. You can pay this much of amount in installments as well. Vedantu has kept an option for that, right? Point number 3. If you are new to Vedantu, you have no idea how the actual Vedantu classes look like. You can take these subscriptions for a month as well, right? You can sit in these batches for a month on the actual Vedantu platform. If you think you are getting benefited, then you can go for the actual, for the 2-year classroom program. First of all, give it a try, people. And trust me, you are going to love it. You're going to love it, and you are going to love it. Trust me on that. And this is the course fee for the 1-month subscription. You need not to pay 2,700. There's a 50% off. You'll get this in some 1,300 something, right? Similarly, this is the course fee for 1 month pro subscription. Divide by 2. Get it. Similarly, divide by 2, get it for 1 month at least. And while enrolling, do not forget to use the coupon code WSPRO. Yes, people, trust me, the study material which you get in the actual Vedantu platform, that is the best study material which you can find across the country, right? Okay, and at the same time, it is going to be your choice to select the teachers, right, and get trained by them. Yes. Okay, the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel. And let me show you at the end how to get enrolled in the long-term batches, in the batches on the actual Vedantu platform, how to get enrolled. See, this is the video which you guys are currently watching. I need to drag this video a little down. If I drag this video a little down, click on this show more. After clicking on this show more, you'll be getting a lot of links. Well, majority of the students currently are looking for CBSE Term 1 crash course, right? There's a link for this CBSE Science Term 1 crash course. If you are looking for it, click on this, right? Click on this, and we have got 2 plans for you, Light and Classic, right? And this plan you are just getting for 1,500. This plan you are just getting for 3,000, right? Choice is all yours. Just join in the crash course, right? In just 1,500, you are getting your entire Term 1 syllabus completed through the crash course on the actual Vedantu platform. And how to get enrolled in this? You need to click on this by complete course. After clicking on this, you need to put your number, your email ID on which you get the OTP and everything, right? Okay, and get enrolled in the crash course for CBSE Term 1, right? This is the demanding one right now, in which I've seen some thousands of students getting enrolled in, right? Okay, if you are preparing for NEET 2023, right? If you are preparing for NEET 2023, I will suggest you guys to go for this link, NEET 2 years. Click on this link. After clicking on this link, you'll be getting 3 courses, Light, Classic and Plus. The choice is all yours, whichever plan you want to take. Well, as I told you, you can try it out for a month. And see guys, if you are trying out this plan for a month, you just need to pay 1,500. That's all. For a month, you'll be sitting in the actual Vedantu platform, in the actual batch, in which you'll be getting trained by the best teachers of the country. Trust me on that, right? You would have seen the JEE Advanced results, right? In Vedantu, well, there were some 1,572 selections from Vedantu, right? I hope you know that. Yeah? Okay, how to get this? Click on this by complete course or try it out for a month. For example, I need to try it out for a month. I need to click on this. After clicking on this, put your number, put your email ID, through which you get the OTP and everything, and by means of which you get enrolled in on the actual Vedantu platform, right? So people, this was all from my side on the tonight's session. Well, there is one important session which I'll be taking tomorrow, which is going to revise your 2 chapters, mole concept and states of matter. Basically, tomorrow I'm going to take a mentee session for 2 chapters, right? States of matter and mole concept. Do not forget to attend that. Yes, do attend that at any cost. It's going to be highly beneficial, and it's going to revise your 2 chapters, okay? And tonight at 10:30, I'm going to take one more mentee on Vedantu JEE English channel, in which I'll be discussing about solid state and I don't know what is the other chapter. I need to see that, yeah? So with this, I take a leave. I'll see you guys at 10:30 sharp on Vedantu JEE English channel, and actually see you tomorrow at 9 p.m. with the mentee. Till then, you guys can take care. Bye-bye. God bless you all. And